I'm very happy to be invited to the DNS. Really excited to talk, and thanks for all spending an hour of your lives listening to me talk about this. So I want to discuss some recent work about Poisson boundaries. Can I work with ground programming? Ground first and do the other. So first, just to set up some notation, let's say G, and for the next 45 minutes, all groups are countable. So G is a countable group, and mu is just some probability measure. G. Given this, we can define a random walk by drawing a bunch of IID increments according to mu and taking their product. So Wn is the product of n IID increments according to the set. Now, given a group and a measure, often when G is non-abelian, you have non-trivial asymptotic events. So you can try to capture these by mu boundaries. They say a measure space P mu is a mu boundary. So it's a measure space equipped with a map from this path space. So this measure allows us to define a map from the space of IID sequences to this path space. The space of sequences, this is, but as you take the sequence GI and just give it to the sequence W. So B mu is a mu boundary. It was equipped with a map from this path space, let's say pi, satisfying the following three conditions. One is that pi commutes with the shift operator on here. It takes some random walk sum path and just shifts it up by one. So your projection commutes with the shift. Two is that this pushes forward the path measure on here. And three, that this projection is G equilibrium. So these are the two. G equilibrium. In particular, 1 and 3 implies that the measure is stationary. So it won't be invariant, but it'll be like an invariant on. So what is the classical example that we have in mind? This is the case for G, let's say it's given, and our measure is a uniform line of free generating set. So, over S in a free generating set, which is -1, which is minus over S. So the picture is just you have 4 valence T. What your random walk will do is it'll, at each step, there are more ways to go forwards than there are to go backwards. So random walk will do something here, it might go forward, but it'll always converge to some random point in this boundary of infinity. So you have a natural boundary, which is just a space of infinite words. This is the natural boundary of the tree. And you have a natural thing measure associated to this, given by the measure of some set A is just a probability you'll converge to something in that. And so your map from your set of cell paths just tells you which point to converge to. So this geometric boundary, space of infinite words, the sitting measure is a mu boundary. So in particular, you get a bunch of asymptotic, so non-trivial asymptotic events. So the event that your random walk will converge to this subtree is non-trivial probability. It's true between 0 and 1. And so another question is this everything. And in other words, is this the Poisson boundary? So you say that B nu is a Poisson boundary of G nu if it's maximal in this space of mu boundaries, meaning that for every other mu boundary, and lambda, so yeah. So B nu is a Poisson boundary if it satisfies the following universal property. So B nu is equivalent to map, and so is n lambda. B nu is a Poisson boundary if for every such n lambda, we have a unique projection. Unique in the right sense. They're all measure spaces. So okay, and so the question is, given a group and given a measure mu, which is admissible, one is the boundary trivial. you have non-trivial events. And two, can you identify it? Can you identify what's on that? Meaning, can you write down some geometric space, with some natural measure, and show that it's maximal in this category? In very natural settings, you can show that in fact, this geometric boundary is often modeled for the Poisson boundary. So this is a topological space. The Poisson boundary is a bridge and abstract measures. So I'll think so. There are dozens and dozens of papers about identifying Poisson boundaries, and I unfortunately can't say all of them. But today I'll just talk about the Poisson boundary identification problem for groups with hyperbolic properties. So some sort of classical results I want to mention. So say indicated molecule. They show that in the case where mu is finally supported on the free generating set, so support mu equals a free generating set, then some boundary, so this geometric boundary equals the Poisson. It's a model for the Poisson. It's generalized by Vernier. In the case where you have finite support, not necessarily a free generating set. And I also want to mention that significant set with Ancona. They did the same thing. They have finite support, but in a more general geometric setting. So not just the free group, they show when B is a hyperbolic group. They showed that the hyperbolic boundary, the Gromov boundary of this group, equal to the any measure, is always a model for this model.
And all these results are not only about bounded harmonic boundary,
Yeah.
right? But they also describe all positive.
Yeah, they also describe it. Yes. But all of these really used in a key way that the measure is finally supported. Like yeah. Okay. So how do you do anything with infinite generations? I should also mention. So the finally supported measures, it's somewhat quick to see that this is always a mu boundary. Like this geometric boundary is always a mu boundary. But even for infinitely supported measures, this boundary at infinity is always a mu boundary. In the following sense, so fit the following theorem. Proved by, well, first in Bergen, the locally compact case, but in the general, like maybe non-locally compact case, it's the theorem of Weyer-Schulze, and also Sebastian Buzel.
But no, in the discrete case, it's also Fürstenberg.
Yes.
Inside the same paper.
So and also Fürstenberg, very possible. I mentioned this because later on in the talk I want to talk about like actions on hyperbolic spaces which are locally infinite, which is why I also want to mention these. So that G acts on X, which is a delta hyperbolic space, and mu is a non-elementary measure. Non-elementary. And random walk always converges to some point in the boundary here. Geometric boundary here. Okay. In particular, no matter what, this geometric boundary is always a mu boundary. You always have a thing measure. So it's natural to ask if, in general, this is also a model for the Poisson boundary. Yeah. And one of the most significant steps in this direction, Kamanovich. So I also want to state theorem of Kamanovich from 94. Who proved it for not necessarily finally supported measures, but also infinitary measures. So he said that mu is an admissible measure. So mu is a measure on some hyperbolic group G. So G is hyperbolic.
And it satisfies the following two conditions. So one is that it has finite entropy, which I will find later, and also that it has finite logarithmic moment. So the sum of log G, UG is finite. So we're finding the subsize. Then, in this case, the hyperbolic boundary of this group with the heading measure is a model for the Poisson boundary of G with mu. And I'll say a few words about how the proof goes, because it's relevant to the theorem we prove later. And the idea is really, it's really quite a beautiful argument. But in order to think about it, I'll have to discuss some of the techniques we have for identifying Poisson boundaries. And one of some of the main general techniques we have for identifying Poisson boundaries is this entropy theory. Okay, so I'll briefly discuss entropy. So say that P is a countable partition. Is a partition of our path space. Well, any probability space, but just in particular this one. Define the entropy of this partition. So the entropy of this partition, maybe we should say rho, is equal to the sum of minus probability of a particular element in this partition, log P, the element of the partition. What it's really capturing is how much information is contained in the partition. So if you draw a random element, one way to think about this is like, one way to think about this is like the number of binary questions you need to figure out which element of the partition you're in. But this really captures the information contained here. Okay. So the main partition that we'll apply this to is a partition given by knowing like the first n steps of the random walk. So one thing to note is that the entropy is always subadditive. So entropy of a measure mu, let's say involved with itself, is always like almost twice entropy of this. So we can always define the following limit: the asymptotic entropy P of u to the n, where n is always well defined, and it's always exists, and it's always non-negative, as long as the entropy of mu is finite. Okay. So now, I think 41 years ago now, in this APP paper from Minor Division Virtue, they say the following entropic condition for triviality of the Poisson boundary. Minor Division Virtue. That assume that the measure has finite entropy, then the Poisson boundary is trivial. Is trivial, if and only if the asymptotic entropy vanishes. So this gives a general technique for identifying triviality of the boundary. But today I'm not talking about triviality of the boundary, I'm talking about maximality of some candidate boundary. So later on, I wanted to introduce some conditional entropic techniques for understanding the maximality problem. Like, given a candidate boundary, when can you show it's maximal? When can you show it's Poisson boundary? So now I'll say these conditional entropy criteria. And one way to say that is really the following. One thing we can observe, we can disintegrate this path measure on our path space. We can disintegrate it as follows: as a measure over your candidate boundary of the space of these conditional measures. This is just the classical disintegration theorem in probability theory. But for each of these things, we can define a conditional entropy. So the conditional entropy of our partition. So the conditional entropy of our partition. Well, it's just the same thing, but with conditional entropy everywhere. So log of this conditional probability of pi times probability, this conditional probability. Right. It's conditional probability of And so Kamanovich criteria, Kamanovich's conditional entropy criteria is the following. So the condition is the following. Kamanovich. Let's say that B nu is some candidate boundary, and you want to ask whether it's maximal. Okay, so we assume that, and okay, if we're here, we'll assume that the entropy of your driving measure is finite. Then this is maximal, so this equals the Poisson boundary. If and only if for nu almost every point of the boundary, this conditional asymptotic entropy vanishes. This conditional asymptotic entropy vanishes. Another way to say it is you can't split up the boundary further. This captures all of the information contained about the random walk. Okay. And so this is a very powerful criterion, and and this is really one of the main tools we have to identify Poisson boundaries. But what Kamanovich did in this paper is better. Like, this is sort of hard to apply in practice sometimes, because you need to understand this random walk condition on a certain point in infinity, and it's hard to do computations. And so Kamanovich introduced two like geometric formulations of this criterion, the ray and the strip criterion. And most applications of this will be through those two geometric criteria. Now, for the second time, I won't state the ray or strip criterion, but I want to highlight one aspect of the ray criterion, just to give a hint of some of the difficulties we have in more general settings. So a typical instance of the ray criterion will be something like this is your base point. This is a point in the boundary you converge to. You show something like this is the random walk, then it's a distance, almost a little O of n of the point here. And so the conditional entropy of this random walk, given this, it's basically pixeling from this ball of size little O of n. So the conditional entropy of Wn, given this base point, is at most log x O of n, which is O of n. Yeah. And so then when you divide by n, take the limits, you get 0. And this is like an instance of how you show something like that. But the issue is, in order to do this, you need some control about the random walk at all points in time. You need something like sublinear tracking. And so you would need some moment conditions on the random walk. Yeah. And so in Kamanovich's identification of the Poisson boundary for hyperbolic groups, you have this finite entropy condition, which is sort of a natural limitation of the techniques. And you have this finite logarithmic moment assumption on the step size of your random walk. And that's more of an artifact of the proof. You apply this strip criterion. And so you need some geometric control of the random walk. And so it's hard to imagine how we would prove something without the moment conditions. So this long term is sort of artificial. And so, and some recent work with Rogani, Fish, and Tielso, we managed to remove this moment condition using sort of new techniques, not going through the ray or strip approximation criteria, but just directly using this like conditional entropy criterion here. So we found a different way to go through here. So I'll say our theorem and then I'll briefly discuss some of the new ideas that go into our proofs. So we use new ideas for hyperbolic geometry, new ideas for probability, and new ideas about how to work with entropy. The first, I'll say that.
One particular but much simpler case, right? That seemed to be known before your work, right? For Sevi group, it was known in general, right? For finite entropy.
For finite entropy in general, yes.
For organic also, right?
Yes. Yeah. Exactly. But there they really use the fact that it's a summary group. They use the fact that you can project to n, you get a random walk on n, and that finite log moment on n implies finite entropy on n. So their techniques like are incredibly specific to the summary group case, which is very interesting. I mean, even for the three semi group, it's very interesting. But even for the three group, like working for general finite entropy measures was unknown. So I'll say the theorem. So say that G acts on X which is delta hyperbolic. Hyperbolic. And let's say the action is non-elementary. Just some natural, like, non-degeneracy condition. Okay. And let's suppose that G has a WPD element. As I'll briefly discuss this condition. But essentially, you need some sort of properness for the action here. And so if the action is proper, then this is true. But this allows for some actions with like infinite vertex stabilizers, like F infinity acting on the scalar graph or something. And so that mu, you measure on G, which is admissible, and has finite entropy. But most notably, no moment assumptions on G. So it can have like really huge steps. Then under this assumption, then the Poisson boundary, so then the boundary of your hyperbolic space, equipped with a Ding measure, is a model for the Poisson boundary. Is a model for the Poisson boundary.
Which boundary?
Oh, so this is the hyperbolic boundary of your hyperbolic space. So this is the geometric space. Now you will converge from random point here. So this is a V boundary. And we show that this is a maximal V boundary. Yeah, using this entropy.
And VPT element was.
Yeah, so
But may I ask you something about this simulation? So your result is extremely interesting already, even for the T group, right, and for hyperbolic group. But this DV, I don't know, the terminology, it seems that your groups is exactly something which is called asymmetrical hyperbolic groups, right?
yes, it's correct. So as a class of groups, this is the same as a class of asymmetrically hyperbolic groups. But the way it goes is like if G acts on hyperbolic space with some WPD element, then it acts.
Maybe it's good
Yeah.
you explain it.
Yeah. I'll explain WPD first. So I'll say here. So you need some sort of properness condition here. Okay. And so maybe. Okay. So H is an element of G. Let's say H is WPD. So WPD stands for weakly properly discontinuous. H is WPD if the following is true. If for every k greater than 0, there exists some m and n such that the k coarse stabilizer of our base point and HM of our base point is finite. So there exists some directions along which you have a finite coarse stabilizer. So the picture is like you have a base point, H is some large power of like some loxodromic element, is H to the M. And you look for the points which move O within some bounded distance and move HMO within some bounded distance. So anything which simultaneously stabilizes both of these, there are only finitely many such elements. So particular, if G is like a hyperbolic group acting on its own boundary, then the action is proper. Any coarse stabilizer is finite to begin with. But for example, if you look at like the infinite rank free group acting on a scalar graph, the action is not proper. You have like, there are infinitely many points here. But the set of group elements which stabilizes two far away elements is finite.
Sweet. So M is M smaller?
So M will usually be large.
Yeah, but lowercase m.
Okay, so yes. Like I've with the same. Yeah, okay, so. Yeah. Yeah, so usually like these 2 points will be very, very far away. So it'll be like, you have to stabilize two very far away points, which is usually hard. Okay, so I'll give you some examples. So, okay, what's true is that as a class of groups, this is the same as a class of so-called acylindrically hyperbolic groups. Group is acylindrically hyperbolic if it has this action, but instead of having some power of H, you just say, for any two sufficiently far away elements, the stabilizer is finite. So it's like it looks acylindrical along some directions. And just as a remark, so if G has a WPD action on some hyperbolic space, then there exists another hyperbolic space on which you're asymmetrical. On which the action is asymmetrical. But I'll state some applications of it, like some groups to which it applies. Okay. So this is new for the free group. This is new even for the free group. For example, it also applies to infinity, because the Cayley graph there is locally infinite. But in order to fix two far away elements, they're only finding many such guys. Yep. This also applies to other groups of interest to like geometers. This applies to like the action of the mapping class group on the curve complex. So this will be like some locally infinite graph. And so this is known to be asymmetrical, this action. So it applies in particular to these.
Can you be a bit more clear on what the exact assumptions are? Does the G have to act faithfully or?
No, not at all.
So I could just take G to be a product, G1 cross G2. G2 is hyperbolic and G1 does whatever it wants.
Oh, but in that case, you won't have a WPDL.
Well, just the G2 itself will have a WPD element.
Oh yeah, I mean this is a stabilizer for the entire group, like the elements of the group which stabilize this is fine, but yeah, so yeah. That's fine.
Okay, so geometrically X will look very much like G anyways.
Yeah, you're like maybe like collapsing, yeah. Exactly. So if X is like relatively hyperbolic, maybe you're collapsing your parabolic subgroups and you get some action here. I should say, like, this notation means the set of group elements which move this point within distance k of itself, and also move this point within distance k of itself, requiring that this set is finite. So that is exactly the properties condition we need. But there's some interesting ideas in the case of WPD actions. But just for today, I'll discuss the proof only in the case of F2, just for the sake of time. Like there are new interesting ideas in the case of F2, and there are other interesting ideas beyond that for the case of WPD actions. But that might be too much for a 45-minute talk. So the issue is that we can't control the random walk at all times. Because without normal conditions, you can have maybe some absurdly large jumps along the random walk. And then maybe you jump absurdly large back, and then you keep going. You won't have any sort of logarithmic or sublinear tracking or anything like that. So we need to find some substitute for geometric control at all times. So the geometric input to our argument is through some recent work of Sebastian Guzel, through what he calls pivots. Okay. So he analyzes like random walks and hyperbolic spaces in a very interesting way. I'll define what we will call pivots, which differs from what Guzel does, but suffices for our purposes. So fix some number n. Okay. Define the shadow of some group element of depth m as follows. So now for the rest of the talk, our group is F2, and the space will be the Cayley graph. Okay, so define the shadow of G at depth m to be precisely the following, to be the set of group elements satisfying the following. So this is the identity. This is your unique path to G, because the Cayley graph is a tree. So you look back distance m. So you go back distance m. So an element H is in the shadow. If the following condition holds, if you look at the geodesic from E to H, this geodesic passes within distance m of G. So you go back, and it's essentially everything in the subtree with some coarse error. This is the shadow. And so you analyze along the random walk. So you say that a time n is pivotal if the following holds. If for all k greater than or equal to n, Wn is contained in the shadow. So Wk is contained in the shadow of depth n, W. Meaning, no, if this is Wn, then forever you're contained in this subtree. Okay. I mean, one of the reasons you expect, I mean, the Poisson boundary captures some sort of stabilization of this geodesic at infinity, and a pivot is precisely a time in which this thing is stuck here forever. So any geodesic along the random walk afterwards has to pass through here. So that is exactly what a pivot is.
May I ask you something about these pivotal points and group? You explained it now, even the free group, right? So pivotal points is a very beautiful argument of Sebastian Güzel in his paper, in his new very elementary proof of Fürstenberg's lemma. So pivotal points are sort of temporary branched points, right? But may I ask you, for your arguments you explained us today, at least in the free group, is it enough to consider just points that really stabilize by Fürstenberg already, right? We know just three, it's very easy, right? We have just three, we have words in our field generated sets, right? And by Fürstenberg, we know first letter, second letter, and so on stabilizes, right? And we know this positive probability from the very beginning, right? You have this branching, and then on all next steps, also again, this positive probability, you have branching, right? Is it enough for what you're explaining just to speak about branching points in sense of Fürstenberg?
So we need some estimates on how long you wait until you see these branching points. And
independently, this we wanted to understand better in your paper. Maybe I'm asking this paper question too early, but I think it would be more elementary if we understand, right? So on the free group, right, we have stabilization, and with positive probability independently at each time t, you have this branching. Is it enough for your consumption to know that it's positive probability and independently we have the branching problem?
with positive probability and independently we have this branching, I believe it would.
Yes, because I think it follows already from Fürstenberg actually, but yes, I'm sorry.
No, but you're probably, that is a very good point. And so the reason we use pivots here, well, it also, we need something like this in a hyperbolic setting, but also in the WPD setting, like the pivots are really key to the argument later on. But you're right, in the case of the free group, we don't, this positive probability and IID branching behaviors. And so what we need is to say something along the lines of, we want to say that many times for pivots. So a pivot is precisely a time when you have geometric control on the random walk. You don't have sublinear tracking, but you have bounded tracking at any pivotal time. So you want to say that pivots are abundant. You have many of these. And so we use the following lemma, or proposition actually. And it's not directly stated in Güzel's work, but it follows from Güzel's work. Is that there exists constant C such that for all n, pivots are abundant in the following sense. The probability that there exists time between n and n plus k, which I is pivotal, is very high. It's at least 1 minus some exponentially the same thing in k. Meaning the time you need to wait until you see a pivot, it behaves like a bunch of coin tosses, like a geometric random variable, really. So with high probability, you're going to see a pivot in any bounded interval or certain length. So not every time will be pivots, but this implies really the positive density of points will be pivotal times. So instead of geometric control at all times, we have bounded tracking at some positive density of points. Okay. And so this is really the main geometric input we use in Güzel's work. And I should say some differences we have here. Like in Güzel's work, pivots are things defined up to some finite time. He has some estimates about the abundance of these. We look at pivots from like infinite time and etc.
Exactly. So there are several very nice things in Güzel's work. He has this elementary argument. He looks on the field until time n, and then he computes, estimates directly the distribution. But after all, one of the things to do with his argument, right? Of course, after all, this distribution shows, not surprisingly, because we know Fürstenberg, not only these temporary pivots until time n, But of course, you can look
Yeah.
on usual periods.
Yeah, exactly.
And maybe we discuss after you
Yeah,
talk,
we-
because I think it really follows from Fürstenberg all the way to that.
Okay, great. So this is the main geometric input. And so essentially what we want to say is something along the lines of, let's say you look at the random walk. So random walk, something daily, it might do a bunch of like random nonsense, it might backtrack a little bit, and make large jumps and then go back. And at these pivots, you know, it's really stabilized. So it might do some other stuff back, then stabilized, and so on and so on. What we want to say is something along the lines of, if you want to understand where your random walk is at time n, and you know where it limits to at time infinity, you want to compare understanding this. Understanding this is really just understanding the distance from the origin. Now, if at time n you're within some bounded distance of this infinite geodesic, then in order to pin down Wn, it suffices to just know the word norm of Wn. And we want to say something along the lines of, this is the word norm of Wn is basically the distance traveled between consecutive pivots. Something along these lines. Okay. And now just to give you a hint about a bit of the entropy argument, I will prove okay, so now we need a different way to do this because we don't have geometric control. All time just has some positive density. So instead of using the Schreiber criterion, we recall the pin down approximation. Pin down approximation method. Not approximation. And what is essentially the following: if we want to show that the conditional entropy of something is 0, it suffices to show that it's smaller than epsilon for every epsilon. I'll give myself a little extra room. Then I want to say, if I'm allowed to ask for a little epsilon of extra information, and given that epsilon of extra information, I can pin down the random walk, then I really have the bound. Okay. So meaning that the following is true. So let's say we have some candidate boundary, me and you, and we want to show its maximum. It suffices to show that for every epsilon, there exists some sequence of partitions, and here's the one, such that the following two things hold. One, that the entropy of a partition, the conditional entropy of the partition, is the most, epsilon n, plus the little of n. Okay. So I give myself a little epsilon of extra information. And if given this extra information, I can pin down the random walk. Maybe with like a epsilon information. That's an epsilon n. Let's go to event. Then this is maximal. Then the new is a percent boundary. So this is really using the conditional entropy criterion, but we don't use like Reyes for approximation. This is sort of a more flexible application of the conditional entropy criterion, which works for our setting. Like this thing only requires really control at so we're able to leverage control at a positive density times in order to do something like this.
Doesn't it just imply that you have
Yeah.
free epsilon or something else?
Exactly.
Okay, so just.
Yeah. Like,
Could you please repeat, I didn't understand the question.
oh, like
It means that you have what?
the entropy of like W.
Just as the usual, basically, they're just, it goes back to just the usual.
Exactly.
Criterion. Yeah.
You're absolutely right. Like this is like this statement.
This is the method to estimate entropy.
Yes.
Of course.
Yeah.
Yeah.
Yeah, we call it this because it's like the philosophy is different. Even though the fact that the statement implies maximality is like you're right, it's just like a
So
one line.
you kind of do it via introducing some auxiliary.
Exactly.
Yeah.
Yeah. Okay, and just to give you a little hint of the philosophy in the approach, so we use pivots, but we also use like this other philosophy to understand. And maybe for the sake of time, I will discuss how you can use this. I will discuss proof of a simpler statement that sort of sheds light on what our argument looks like. So I will prove the following statement in a way that resembles our argument for hyperbolic groups. So say that mu is a probability measure on the integers with finite entropy. Then the asymptotic entropy vanishes. Now, this just follows from the entropy criterion plus the fact that Poisson boundaries of Z are trivial. But I will prove this in a way that says like, no. So here's a proof. First, assume that mu has bounded support. So at case one, if the support mu is in some bounded interval, we know that the random walk is just some number in this interval minus nd to nd. So the entropy of this thing is just log of the size of this set. It was the most log 2nd, which is sublinear. So now for the more general case, what we want to say is that in the more general case where you have finite entropy, you can compare to the finite support case in a reasonable way. So case 2, just the general case, the entropy is finite. We want to show that the entropy of Wn is at most epsilon for every epsilon. Okay. And when we do this as follows, we pick some threshold d, which is much greater than 1, and d will depend on epsilon. Okay. You pick d large enough, so the probability of having an increment larger than size d is very, very small. Then, you draw your random walk in the following way. So you draw your increments gi. And now if gi is larger than d in size, you record exactly the increment. Like this is some huge mess. You just record exactly what this information. Yep. Otherwise, if g is smaller than this in size, you don't record anything about g. You just record the fact that it was small. Say it's small. Yeah. Now, what is the point here? Because d was chosen large enough, the entropy of recording the bad increments is small. The entropy of this is the most epsilon n. And using this information, we can reconstruct the random walk. Okay. So what do I want to say? The random walk of time n is precisely a sum over the bad increments. So over the large increments of gi plus the sum of the small increments. Oh, these are the increments of the random walk. GIs.
Random walks where?
Oh, so this is the random walk on just Z now.
On Z.
On Z.
Yeah.
Yeah. Okay. Yeah. This is the sum of the small increments. What is the entropy of recording this? The entropy of recording this is the most epsilon n. And now, what is the entropy of recording this thing? Now, this is just some number. Negative nd, positive nd. And so the entropy of recording this is most log 2nd, which is sublinear.
So for the very large increment, the entropy is close to 0, right?
Yeah, for each individual increment, the entropy is close to 0 because we obscured so much of the information.
But even with them all together, wouldn't be, so in your argument, can't you assume that there are no huge increments greater than something?
Maybe there are. Without moment conditions, we can't assume there are no. Yeah. So this is just some finite entropy measure, no moment conditions, and so maybe there are some huge increments. But we just pick d to be some number, which is just a threshold, defining what increments are big and which ones are small. And the point is, for each of these, the entropy of recording this is close to 0, but maybe we record some linear number of them. Maybe some positive density of times will be large. Okay. And the point here is that recording the entropy of this is at most epsilon n. So this is actually a bit of information. If I allow myself to record an extra epsilon of information, I'm allowing myself to record the big increments. And then, given the small increments, I make a bunch of entropy savings. And so that's really the philosophy of this pin down approximation method. And now I'll just say a few short sentences about the argument in the free group case, and then I'll conclude. Just to state exactly how we modify this. Okay. And so the idea is really the following. We're going to split up time into a bunch of intervals. So we split up time, 1, the n into a bunch of intervals. So 1 up to some special alpha, which is very, very large. And then alpha plus 1. To alpha up to n. Okay. Such that, so alpha is chosen large enough, so that with very, very high probability, in this interval you see a pivot. And with high probability in this interval you see pivot, and so on and so on. Okay. And then we pick d, depending on alpha, and depending on epsilon, such that with high probability, the size of the increment is less than size d. See, we split up time into these chunks. And what we do is, if you have a pivot in here and a pivot in here, then to know the random walk, you just need to record the distances between these two guys. Now, recording the distances between consecutive pivots, that's just recording the length of the thing between the pivots. Right, both of these are within some distance to the geodesic. You just need to know their length. Now, according to the length, if all of these increments are size in both d, then exactly this type of thing happens. According to the length of that is sublinear. Okay, but maybe some positive density times you don't see pivots. And if you ever have an interval where you don't see pivots, you just record exactly on the nose every single increment. This also, you require a little epsilon extra information in order to do this. So it's exactly this picture. Now, sometimes you see a pivot, sometimes you don't. Maybe between here you did something huge mess. And some 1% of the time you really lose, and you really have to record with increments. Now, that's just the philosophy of the pin-down approximation method in the case of the group. And there are other interesting geometric and probabilistic ideas in the WPD setting. You know, the fact that the space is non-proper, but just for the sake of today, I want to end here. So just thank you all for listening.
Thank you very much. Yeah. I don't know, so we have to.
Could you extend this to locally compact groups, or is it far-fetched?
I don't know if it's far-fetched. I mean, I haven't thought much about extending this to locally compact groups.
But locally compact with some hyperbolic properties.
Yeah, but some hyperbolic. You need some hyperbolic.
No, sure, of course.
But like,
Acting on some hyperbolic space, yeah, sure. Because recently, I think 2 of your co-authors, they extended the strict criterion to locally compact groups, so.
yeah, I think that makes sense. Yeah, I mean, you need to work with entropy and locally compact groups. And I personally have not thought much about it, but I wouldn't be so surprised if something like that. Yeah, that's a good point.
That's a small technical question that I was asking you again about huge increment. Your entropy is finite.
Yes.
And then whatever space you have, well, if entropy is finite, of course, on some tail, entropy is close to 0. And then for asymptotic entropy, it seems that one can always ignore them in our estimates, very huge increments.
I don't know about that. I mean, well, for each, you pick your threshold large enough so that at each particular step, you have some very, very low probability of seeing this like large jump. This has entropy close to 0, but the entropy is not 0. And this is at each increment. So maybe the entropy of this thing is epsilon.
But you have n increments and the entropy is not great on these large increments, wouldn't be smaller than epsilon times n then, and epsilon is small.
Yeah, exactly.
Then in some sense you can, well, in this sense you can ignore it.
Yeah, exactly. And that's what we do. Yeah.
So your main goal would be some not too huge increments, right?
Yeah, that's where we make all of the entropy savings. Like all of our savings are in the increments which are small and between pivots. Yeah.
No questions or remarks? If not, then we have a 20-minute break till the last talk is 4:15. Thanks again.